So just for context, figuring out how proteins fold their 3D shapes using computers.
Yeah.
That's always been hard, hasn't it?
Oh, incredibly hard. Traditionally it's involved these super complex calculations. Takes a very long time.
A very long time. Like, what are we talking? Does it slow things down, say, for making vaccines?
Absolutely. It's a massive bottleneck. I mean, think about needing a vaccine quickly, like in a pandemic.
Right.
If your computational methods take, years to train the AI or millions of simulation steps, that's a real problem.
Yeah, that delay could be critical, which makes this intense sim result. You said 34 generations for convergence.
Just 34?
Yeah. So that sounds like revolutionary compared to years or millions of iterations. What's the secret sauce there?
Well, this is where it gets really interesting. They use a different approach involving what they call agents.
Agents?
Yeah, computational agents. And they're guided by, get this, circles of intention.
Circles of intention.
Okay, and something called an instructional field pressure. The key thing is, these agents aren't just crunching numbers randomly. They seem to be learning meaningfully.
Learning? How so?
Intensive calls it a compression heuristic. It's like they're finding the most promising paths to the right protein shape much, much faster.
A compression heuristic, so less brute force, more intelligent searching, like finding shortcuts.
Exactly, a highly efficient search. And because it's so efficient, they're suggesting it might actually be a whole new mode of computation.
Wow, okay. A new mode, what are they calling it?
Intentional folding.
Intentional folding, that's quite a claim. What's the proof? How do we know this intent thing is really, doing something?
Well, the main proof point is just the sheer speed and efficiency. I mean, getting those results so quickly suggests intent isn't just a label, it's actually working as a parameter in the computation.
Right, the results speak for themselves, basically. And the circles of intention, how do they help?
Think of them as focusing the agent's attention. Instead of looking everywhere, the circle guides it towards interactions that are more likely to lead to the desired outcome, the intention.
Ah, okay, so it narrows the search space, stops the agents getting lost.
Precisely. It's a core part of that compression heuristic, letting them learn faster with fewer steps. Targeted exploration, not just random wandering.
Makes sense. So speed, the circles, and this idea of intentional folding is maybe a new computational principle.
Yeah.
That's the core evidence.
That seems to be the thrust of it, yeah. It strongly hints that maybe computation can work differently if you build in this kind of goal-directedness.
And the sources mentioned this idea, intent-driven logic, might be bigger than just protein folding, a better way to compute complex stuff in general.
Yes, exactly. The success here seems to align with this broader idea that maybe embedding intent makes computation more powerful for really hard problems.
And they've tried this on other things besides proteins, right? I saw mentions of other diseases.
Oh, yeah. And the results there are maybe even more eye-popping. They applied similar intent-driven simulations to, for instance, HIV latency.
Okay, that's a tough nut to crack.
Incredibly tough. They reported achieving near total eradication of the latent virus in just 20 adaptive cycles in their simulations.
20 cycles for latent HIV, that's huge. What else?
Well, they looked at cancer, reporting near perfect optimization in 25 cycles. Diabetes, near optimal results reported. Even Alzheimer's showed effective convergence.
Wow, cancer, diabetes, Alzheimer's, HIV. That's quite a list. It really does suggest this isn't just a one-trick pony for proteins.
It really does. The consistency across these different, very complex biological problems. It strongly suggests that this intent-driven logic is a powerful, maybe general-purpose tool.
A new scientific methodology, they called it. Intent-based learning.
That's how they're framing it, yes. A new way to approach these problems computationally.
Okay, so let's circle back to the vaccines. Protein folding vaccines. What does IntentSim mean for them specifically?
The implications could be massive. First off, speed. Imagine dramatically cutting down the time it takes to find the best vaccine candidates.
Right, identifying promising targets way faster. Especially useful if a new virus pops up.
Exactly. Instead of months or years, maybe, much quicker cycles of design and testing. But it's not just speed.
Oh well.
Precision. The level of control might allow for designing truly personalized vaccines.
Personalized. How would that work?
By modeling how a specific protein antigen folds and behaves in your specific biological environment, you could potentially design a vaccine tailored for maximum effect and minimal side effects for you.
Okay, that really does sound like the future, tailored vaccines. And I think I saw something about modeling how proteins change shape inside the body.
Yes, that's another key aspect. They can model how the folding pathway adapts to the cellular environment. This opens the door to designing vaccines that are sort of dynamically adaptive?
Dynamically adaptive, like they adjust themselves once they're administered.
Potentially, yes. Vaccines engineered to work best in the specific conditions they encounter inside the body, making the immune response stronger and more targeted, almost like a smart vaccine.
A smart vaccine, amazing. Now, you mentioned they might integrate this with existing tools, like Rosetta.
That's the idea. Rosetta is fantastic for detailed, high-resolution molecular modeling.
Right.
So the vision is a hybrid system. IntentSim provides the high-level intentional guidance pointing towards the most promising directions, while Rosetta handles the fine-grained structural details.
Best of both worlds, then. Intensim's smart search guiding Rosetta's detailed work.
That seems to be the goal, leveraging the strengths of both.
Okay, let's get slightly more technical for a second. The sources talked about a quantum intent framework underneath all this. What's the basic idea?
Right. So the agents, these computational agents we mentioned, they start out sort of, considering many possibilities at once. They call it a quantum-like superposition.
Like exploring multiple solutions simultaneously.
Kind of, yeah. Multiple intents or parameter sets, different protein shapes, different antigen designs, whatever the problem is. They cast a wide net initially.
Okay, wide net. Then what? How do they choose?
They evaluate these different intents using specific scoring systems called objective functions. These are tailored to the problem.
So, like for a vaccine, it might score how well it binds to an immune cell. Or for folding, how stable the structure is.
Exactly. They test all the possibilities against these criteria. Then the agents collapse their state to the best option found so far.
They pick the winner, essentially.
Right, but it's not over. To avoid getting stuck, they then introduce small variations, mutations, to their chosen intent.
So they tweak the solution a bit.
Yeah, to explore the nearby possibilities in the next cycle, looking for even better solutions. It's this iterative cycle. Explore widely, evaluate, select the best, then tweak and explore nearby.
It sounds, well, very efficient. Exploring, focusing, refining.
And the results, the speed and accuracy they're getting in protein folding and these other areas really seem to back up the power of this approach. It feels like it could genuinely change things in biomedicine.
And maybe even change how we think about how things get organized in biology, that idea of intent.
It certainly makes you wonder.
So, wrapping this up, the big takeaway for you, the listener, is that IntentSim seems to be a major leap. Using intent computationally is giving these incredible speedups for protein folding and potentially vaccine design.
Exactly, and that translates hopefully into faster development of better vaccines, maybe even personalized ones down the line. It's got huge potential health implications.
It really does. And it sparks that deeper thought, doesn't it? This idea of intent in a computer. Does it tell us something about biology itself? Does it challenge how we normally think about these processes?
It really does. You know, some of the other material you shared mentioned this concept of an information intent nexus.
Right.
The idea that maybe there's some inherent drive or directionality in how information organizes itself in complex systems, including biological ones. Is IntentSim just tapping into a computational version of that?
A computational analog of some natural principle. That's a pretty mind-bending thought. Like maybe the universe, or at least life, has this underlying tendency towards certain outcomes.
It definitely encourages a different perspective, perhaps
Yeah.
thinking about things in a more dynamic, maybe even goal-oriented way.
Well, definitely something to chew on. If you want to explore this more, intentsim.org is the place to go, it sounds like.
For sure.
Really makes you think about where this new mode of computation could take us. Thanks for joining us for this deep dive.
Absolutely. Fascinating stuff. Until next time.